bytecode interpreters in particular fast. All right, sure.
Okay. So thanks for having me. Today I'm going to talk about multi-level quickening, which is something that I worked on about 10 years ago, and which still has a lot of interesting features that I think lend themselves well for future work. Before going into the talk itself, I have two preliminary slides. One is because I think in this kind of research, this actually was an influence, is how science progresses through paradigm shifts. There is this great book, it's called The Structure of Scientific Revolutions from Thomas Kuhn. It's from 1962. And it's probably too much, it's a complicated read because it's mostly about physics, but there is like an easily accessible 95-page summary in front of any modern edition of the book. And I'm pretty sure every university library has it on file. And what Kuhn basically discusses, he says that there is, normal science is progressing, and usually people arrive at anomalies, and these anomalies cannot be explained satisfactorily by the existing paradigm. And so what this then, of course, means that when much of these anomalies accrue, you actually have to do a paradigm shift to re-examine the foundations and devise a new paradigm that is factoring in all of these anomalies to explain also those satisfactorily. And later we're going to see that in my work in interpreters, in the beginning, there were a couple of anomalies that were not explained by the existing model, and we needed a new model to actually explain how interpreter optimizations work. And the second part that I wanted to present a brief overview over the anatomy of interpreters, just so that we're all on the same page. I have 4 words that I'm using. Mostly the third one is relevant, and on the left-hand side we have a small interpreter that I'm going to discuss so that everybody knows what everybody's talking about. So on the first slide I have here, can you see my cursor?
Yes. Yeah.
Yes. So we have an interpreter routine, so that's basically all of this function here, that it basically has a code object and some stack data representation, and then it starts looping over the bytecode and dispatching the instructions. So we have an instruction add and a load here. That's what we refer to as an interpreter routine. Then we have instruction decoding. That's mostly this part where we get the opcode by the instruction pointer. So we basically dereference the instruction pointer to see what opcode it has stored, and then advance the pointer. Depending on the bytecode format or the interpreter format, there can be also optional decoding of the arguments, but that is something that we call as instruction decoding. Then we have instruction dispatch. That's usually what we refer to as decoding plus the switch statement here, so that we, based on the opcode, go to either add or load, probably not to default because there would be an error. And then we have the final part that I think is also interesting for clarity's sake, is interpreter instruction implementation. So that's basically in the add instruction that would be getting these operands from the stack and then pushing the result. And also here for this load, we have some object that we push onto the stack. The break itself is already belonging to the instruction dispatch. So basically what instruction dispatch does, it makes sure that you go from one instruction to the next instruction. So that's decoding and dispatching. Okay, so let's now talk about the progress in interpreter optimization. So that's some of the stuff that I did in the 4 years between 2008 and 2012. I did a little bit more afterwards still, but that's basically the core area that I'm considering. And also some words of caution maybe in the beginning. This is obviously my subjective interpretation of having been there at the time and doing the work. It does not say that somebody else did not do anything else that could have been relevant or did something similar. This is just something that I'm talking about the way I see things. So multi-level quickening, the stuff that I'm at core talking about, is merely the end product of a sequence of much smaller steps. So the first steps in the 2006 to 2008 timeframe was to realize that the existing models of interpreters did not explain the varying optimization potential. So this is something that I needed to wrap my head around because there was some conflicting evidence, and we're going to talk about that later on in detail. From 2008 to 2010, after I understood what the performance problem really was, I worked in the beginning on this efficient inline caching in CPython, which actually today I found out is in CPython. So they seem to have adopted some of these techniques, and they are using that. in CPython, and then from 2011 to 2012, so after I moved to the States, I looked into this multi-level quickening, and we're going to talk about it in detail. So up until 2008, or in 2008, the existing model of interpreter optimizations are inadequate. And the problem basically was, the way I look at things nowadays, is that most of the existing models of interpreter optimization say basically, oh, they are efficient interpreters, and everything else is just a slow interpreter. And nobody cared about those slow interpreters too much. They were just slow, and that's about it. And unfortunately, this model of interpreters is insufficiently powerful to describe the varying optimization potential of instruction dispatch-based optimizations. So that's something that we're going to talk about. So threaded code at that time was the predominant interpreter optimization. It's quite easy to implement, and the reported speedups are quite good. So for efficient interpreters, you could get up to 2x performance improvement by using threaded code. Unfortunately, however, there was conflicting evidence, because the implementation of threaded code in Python, for instance, it had roughly 20% performance speedup. I think I remember it was actually only 14%. And then there was this amazing paper from 2004 from Vitale and Abdelrahman, and they basically had some tickle programs where they also applied threaded code, and they found that sometimes there was even a slowdown. So it didn't really optimize that much. And nobody really understood this, because the people who worked in dispatch-based optimizations, they focused primarily on efficient interpreters and not so much on the slower ones. And much more, the instruction dispatch could possibly be the only source of slowdowns here, because when you go from threaded code to switch dispatch, you'd get about a 2x performance slowdown, whereas the inefficient interpreters were 100x to 1000x slowdown. So the instruction dispatch should have reduced this to a 50x slowdown if and only if that would actually have been the key source of performance impact. So this, I think, is at its core a classical instance of this Kuhnian scientific progress. There was a progress in interpreter optimization, but this progress revealed conflicting evidence, these anomalies that I've talked about. So clearly this varying optimization potential is an anomaly that should not have been expected if this was the only source of slowdown. And the single model that we had did not actually explain the evidence in any kind of they didn't even consider that a problem, because it was just slow. And so this was kind of a posteriori clear that this is a paradigm shift that's needed. And this is something that I worked about in the beginning, namely I formulated this new model that focused on high versus low abstraction level interpreters. And we had these high abstraction level interpreters like Perl, Python, and JavaScript. And then we had these low abstraction level interpreters like Java, Forth, and OCaml. And I think it was the crucial step here was to consider the instruction implementation complexity. So that is actually something, once you understand how this affects performance, it's quite clear that instruction dispatch is not the right optimization technique here. So these are some slides that I did in 2009. I have a small paper, probably not that. I think the only person who cites this is Carl Friedrich, by the way. It's on the left-hand side, we see this high abstraction versus low abstraction model. And the idea is at the lower side, at the x-axis, you see that the number of assembly instructions is needed to implement the interpreter instructions. So you see, for instance, for Java, OCaml, and Forth, oftentimes you can implement what is supposed to happen in a machine instruction. So a classical example is a Java I add instruction, an integer add, and you can mostly implement this directly in an Intel 32 or 64-bit architecture. Whereas if you look at this Python, Lua, Perl, Ruby, and so on and so forth, interpreters, you'll find that oftentimes their implementation is much more complicated, requiring tens, sometimes even hundreds of native machine instructions. And what this model actually did, it said, you know, if you have a high abstraction level interpreter, you can basically cut down interpreter implementation complexity. So you move from high abstraction to low abstraction level, and then afterwards, the instruction dispatch-based optimizations, they will be then highly relevant. So these low abstraction level interpreters, like I said before, they were dominated by dispatch costs. you can obviously use sometimes a single machine word to implement the instructions, but then you need 8 to 9 instructions for a switch dispatch and 3 to 4 native machine instructions for an efficient instruction dispatch in threaded code. So the performance benefit is you're halving the dispatch instructions and you get better utilization of branch prediction hardware. That's where the 2x performance improvement is from. In high abstraction level interpreters, however, this cannot be the case. And you have these overheads because you have dynamic typing, you have complex data types like unbounded range integers, you have reference counting, boxed objects, and so on and so forth. And thus, you need to focus on these things to actually get to the performance. By the way, if you have any questions, please interrupt me. I cannot see the video streams of you guys, but if somebody screams loud enough, I'll stop. So these are the high abstraction level interpreters, and they are dominated by the instruction implementation. So let's look at some of the stuff that you can do to optimize that. So here I have a very simple example. I used it in my papers all the time. It's a simple Python function. It has this addition function that has 2 arguments, A and B, and you return the addition of those. And in bytecode terms, in Python, what you'll see, it has this code sequence takes 4 bytecode instructions, 2 of these load fast instructions for the arguments A and B. You have the binary add, and then you return the value. And at the lower half, you see the implementation. You can clearly see that this is an untyped or typed generic instruction. So you're popping the right argument from the stack. You take the left argument as the top of stack element, and then you're calling some generic pi number add function with left and right to get the sum, set the sum, have some reference counting, and dispatch. So this is like the classical CPython implementation for a binary add. And if you look in the JavaScript implementation, it's a little bit more refined, but it's roughly the same stuff. If you look at the performance, you'll find that if you add threaded code to this interpreter, you get, in these experiments that I did, roughly up to 30% performance improvement. Sometimes it's a lot less. So for this IDS benchmark, it's about 0.5% or 5% that you can get for performance. So that is roughly already indicating this conflicting evidence that I hinted before. If you then go into something like inline caching to counter the dynamic typing effects, that's something that I did in 2009 and 2010. The idea is if you go back and forth, you see that I've replaced this binary add with a long add instruction. And you see in this long add instruction already, if you take a look here, there is the operand stack magic, but here I already have an inline type check for both arguments to see whether those are really integer numbers. Otherwise, I'm just doing some de-optimization stuff. But then I can directly inline the long addition for left and right operands. So I will basically shortcut all of the evaluation logic in inline caching that would have been done if I called pi number add. If we take a look at performance, we see that this already doubles the impact that we had. Before we had roughly like 30%. So that was the best we could do roughly before here. And you see that now we can get almost up to 2x performance improvements in some of the benchmarks. So that's like the first step already. In multi-level quickening, we basically take this one step further. So the idea is then to not replace one instruction, but to replace all the instructions that are combining in this computation. So you see we've rewritten the load instructions and also the return instruction. And here I have the 3 different implementations that we need here. So we have this long load here, and we basically moved from this NAMA add instruction, the type check, to the long instruction, to the load instruction. So here we have the type check, and we have an unboxing. So you see here that after this execution, or after executing long load, not a pi object is on the stack, but the actual numeric representation of this number. So we have 2 native machine numbers here written here on the stack. And then we have this addition instruction that is then still popping the numbers off the stack. But then we basically also use the native machine, or what the compiler generates here, to actually add the numbers x and y together. And you can also see there is no reference counting anymore, and there's no function call anymore. So this is now basically almost an equivalent of an IAD instruction for the JVM. So we've basically moved from Python semantics in high level to very low level semantics here. And then we have the load, the return function, and the return function here is basically the same. It only takes what's on the stack. It knows that it's a native machine type number. It boxes it again for the type that we're expecting, and then it basically returns this value. If we had a store function here for the stack, the store function would also box the numbers first. So there is this notion of something that starts a sequence and something that ends a sequence. And when it starts, it does all the unboxing, and when it ends, it does all the boxing again. But this is now only the first part of multi-level quickening. Now is actually, we have the performance results here. We see that we add another 2x or up to 2x onto the 2x speedups that we had before. So now we're at 3.5 and almost 4x speedups here. And what we realize now is that this is now a situation where instruction dispatch becomes an important cost again. And so in the second part, I concatenated these sequences. So these are 4 instructions now. So I concatenate all 4 into its own super instruction. This is, for instance, super instruction 1, 2, 3. And then I only need to set the first one because it then takes care of manipulating the interpreter state so that the interpreter thinks it's executing all 4 instructions. And you can easily see now we added another 2x performance increment or improvement onto these interpreters. So if we take a look at the performance, we see that with this multi-level quickening, we went from our baseline, which is like a 30% speed up, first to about 2x, then to 4x, then to 6x speed ups with this technique. Obviously, not all the benchmarks are benefiting equally, but the ones that are particularly sensitive to interpreter optimization, they benefit a lot. Okay. At this point, I want to highlight how we go about benchmarking interpreters. And I think something that was quite nice in the original MLQ paper and that hasn't been done in the past 10 years, to the best of my knowledge, of course, is that I tried to go the extra mile to understand the performance potential of benchmarks. Because often when I optimized the interpreters, I found that programs that are not really constrained by the interpreter will not benefit from the optimization. So basically no amount of optimization I did eventually make sense performance-wise. It did not turn out to optimize the program that I wanted to optimize. And so something that I did, I recalled a chapter in my favorite computer architecture book. It's a Computer Architecture Quantitative Approach from Hennessy and Pedersen. Actually, I think I still have it around here. So this is actually really the book that I looked it up. The idea there was to basically focus on the corollary to Amdahl's law there. It's basically a fractional performance rule. It says that the maximum possible speed up you get is basically due to the time you spend in that amount. So for instance, if I have a program that only spends 10% of its time in the interpreter and I double the performance, so it basically goes, instead of 10%, it now only takes 5% because I doubled the performance. But overall, you only see that the program gets faster by 5% because all the other stuff wasn't really something that happened in the interpreter. And so I think this is a great way to take a look at the benchmarks, understand how their performance potential will work out, and then figure out how your interpreter is going to optimize this. Okay. Another thing that I wanted to mention is that MLQ is not only limited to numbers and scalar data types and operations. Besides this, I already had also attribute reads and writes, subscript reads and writes for some numbers, and MLQ is in general not really tied to the numeric stuff. It's just something that's easy to show. Okay, where to go from here? I think with respect to future work, I have a couple of ideas in mind. Some of them I already started working on a couple of years ago, but never came around finishing it. But I think there's some interesting stuff. The first part that I always found interesting is that in interpreters, you cannot do this in hardware, but it's very easy to do in software. You can have hybrid instruction set architecture interpreters. So what you can do easily is now we have basically three levels of multi-level quickening. First, the inline caching, then the multi-level quickening, then the super instructions. But you could easily have another third level before the super instructions that basically replaces the stack-based instruction set architecture with a register-based instruction set architecture. So the rewriting is kind of simple to go from stack-based to register-based. And the advantage there would be that we could save another 30% of instruction dispatch overheads. So this would also translate into roughly 30% speedups here. So this is something that is interesting, hasn't been done to the best of my knowledge, and gives you guaranteed speedups post the stuff that's already in the paper. Another thing that I always found interesting is that you can have feature adaptive interpreters. So most of the interpreters that are out there, they analyze their programs and optimize the most frequently occurring case, similar to a JIT compiler where they say, okay, make the common case fast. In this case, however, if you have many different, you can have multiple different interpreters that you're optimizing in between. And so you could also analyze or specialize cases for all special cases. So this is, I think, quite relevant for functional and logic program or logic-oriented programming languages. So for instance, in functional programming, you could special case for frequently occurring current functions. So you can have, for instance, a derivative that says, okay, from between 0 and 10 arguments, I have like 2 or 3 different variants of optimized instructions that cover all of these areas. And then you can get basically, you could reduce the function call performance impact. I'm also not sure whether this has been done, but I don't believe it has been. Cross-native machine library, multi-level quickening, that is, I think, super cool. And I already started working on this in 2014, 2015, but like I said, it wasn't really finished. Is that traditionally what you have is that there is an optimization boundary between native code objects. So you have, for instance, the JVM, it's calling out to via the Java native interface or a foreign function interface to any other native machine library. And as a result of that, you'll find that the optimizer is not including the native code that you see across the foreign function interface. And so what this means is that some of the parts, if you, for instance, use NumPy heavily in PyPy, they needed to special case this behavior such that they could also work with PyPy, but with NumPy. But in this MLQ style of doing things, you could actually provide an API, like an optimization API, where foreign libraries could register their special case logic. So what you could do is you could, the abstract interpreter that's already in MLQ could stay the same. So it would also stay in MLQ as is. But then a library like NumPy, it could register its own optimized code within this API. And thus you could, across native machine object boundaries, across optimization boundaries, you could still perform optimizations. That could actually be in an arbitrary complexity. So it could very well be that libraries like NumPy, they could actually tell us their own super instructions. So it would go not only the not the data types and the single derivatives, but actually directly super instructions that take care, that they find that they are using frequently. I think generic hidden classes could also work with multi-level quickening. I'm not aware of anybody working in that domain yet. Hidden classes themselves, I cannot go into the details here, but it's a very well-known optimization technique in JIT compilers. But there are no interpreters that make the use right now because performance is not really that beneficial for an interpreter yet. But once you get to MLQ-style interpretation, the performance becomes a bottleneck. And so for generic hidden classes, it's actually easy in the interpreter because the only thing you need, you basically have adjacent memory blocks that are just regular arrays with pointers, and then you have additional MLQ instructions that know basically that the third element of an object is an integer. So basically you ship a couple of specialized instructions, and then you get highly optimized code to deal with these object interfaces of these classes. And finally, I think the generation of MLQ-style interpreters is something that's super interesting. So at TU Wien, where I got my PhD, there was this VMGen and Tiger project. Tiger was later done also by David Gregg in Trinity College in Dublin. And in MLQ, it's quite often the case that you have a lot of the derivatives. So you have binary add, and you basically cut and slice binary add to get your code blocks and your data elements so that you actually can use them in derivative instructions. And so once you have this idea and once you understand these derivatives, what you can do is you can generate all of the instructions that you need. So for instance, in Python, that would basically be you only would need the numerical tower of all the data types plus conversions and operations. And you would also need the additional operations to enable boxing and unboxing. So this is something that I think can easily be done. And then finally, I have 2-3 philosophical observations that I always found interesting about this work. If we have the time, I would still like to go into those, but if we're short on time, I can just skip due to our technical difficulties.
Yeah, it's fine.
Fine, okay. Then I'll hurry through those. Most of my grad students think they are super interesting. That's the only reason I'm talking about those. So I've been thinking about this interpreter optimization stuff for a long time. So every now and then I still have a student in a master's thesis that works in that domain. And I have 3 kind of interesting ideas about this. One is an information theoretical perspective of interpreter optimizations. Then I have some thoughts concerning the limits of interpreters versus JIT compilers that are already like over 10 years old, but I made a scan for this talk today. And I have some other thought, like just a minor thought, but still interesting, on multi-level quickening in general for virtual machines. So the first one is an information theory idea for regular interpreters. If you think about an interpreter, what it does, it only has instruction dispatch. So it has this idea of a next relation, and it only tells us to go from instruction I to instruction J. So the only thing that this relation encodes is just the sequence of instructions in the interpreted program, not the static ones, but the dynamic ones. But this is the only thing that this next relation does. It goes from I to J, from one instruction to the next. And if you think about inline caching here, it not only tells us something how we get from instruction I to instruction J, but it also tells us something about the expected types here. So this is why there's this Greek tau letter here. So it says, oh, in the example that I showed before, I go from load fast to long add instead of binary add. So this encodes in this next relation, in this one jump that the interpreter necessarily needs to make, the additional information about the expected types. And then again, if you go to MLQ, you enhance this information that is piggybacked onto the next relation by not only encoding what instruction is next, but also the expected types and the data representation row. So it tells you exactly that the top of stack element is a uint 64, or it can be any other type that you're designated. But this is already encoded or overloaded through this next relation. And I always found this interesting because it means that control flow that's usually happening within the instruction J can be lifted to another level, namely into this next relation, because the next jump you always need to make. There is no way around this, but you can add more and more information on this, and this it benefits performance. So this is what I also tried to highlight here is what's the next step? What is the next subscript that we can add to next, such that we can add more and more performance onto this, or optimize the interpreter more and more. The next part that I've showed on the limits for interpreters compared to JIT compilers, for this talk, I went back to my office last week and dug through all of my research notes, and you can believe me that there is a shit ton of them. And I found this one that's also something that I've shown my grad students for the past 5 years. It's from April 7th, 2010. And this is basically the core insight that I had that was responsible for this multi-level quickening. And what it does in my ugly handwriting is basically says that it doesn't really matter what the JIT compiler is doing. There is always a correspondence that's on the lower half, this A here, between any optimizations that a JIT compiler can do by the process of quickening, of rewriting instructions. I can always lift, regardless of what the JIT compiler is doing, can always lift this to the virtual machine level. I can always have bytecode instructions and derivatives here, so that's optimized bytecode instructions that do exactly the same thing. And on the next slide, I have this, I went into this a little bit more, is assuming that there are multiple optimizations level, so optimization level 1 and 2 here, we see that if the JIT compiler goes from the bytecode instructions through some successive optimizations, it doesn't really matter how many there are, it optimizes these native machine codes, then for each of these optimizations it can do, there is always a possibility for an interpreter instruction to also do this. So the interpreter instruction can also mimic the whole optimization process. So that's why this multi-level quickening is something essentially that a JIT compiler would also do, but I can do this also on the interpreter level. And so on a fundamental, kind of a fundamental theoretical perspective, the interpreter can always do everything that a JIT compiler can do. So it's not, there's no theoretical limit superimposed that says you cannot do this in the interpreter, but you can do it in a JIT compiler. So that's a way, an interesting way to think about this is what is an effective optimization in a JIT compiler? And once you have identified those, you can move those, you can lift those to the interpreter, and that gives you a nice, purely interpretative way of thinking about this. And then a nice side effect of this is that all of the stuff that you do in the interpreter will be compiled or will be built into the interpreter when you compile it. And because you compile it with an ahead of time compiler, it may actually end up being more optimized than what the JIT compiler would do, because at interpreter compile time, the ahead of time compiler has basically, there is no latency problem. It can take 10 hours to compile the interpreter. I really don't care how long it takes, as long as the code that gets out of it is optimal. And because of this theoretical concept, I think theoretically there is no limit, but there are practical limits and constraints that you need to consider. One of them is that you are severely limited by the maximum number of interpreter instructions. And I have only anecdotal evidence here. I didn't ask the person who relayed this information to me to cite his name publicly, but I know a person who tried to build an interpreter with 2,000 instructions, with 2,000 case statements, and at least for GCC version 2.5x or so, that just crashed in their compiler. So the compiler could not compile a program that had more than 2,000 cases. There was just deemed to be the maximum possible case. I hadn't replicated this, but I believe that it probably makes sense for compiler writers to assume n upper limit for an interpreter. And so the best number I have is like 2,000 is the maximum you can do. And this obviously puts limits on our interpreter optimizations. And the second part, and I find that is also something that usually is hard to understand for students, you have to speculate on derivative utility. So what this means is that derivatives are these optimized instructions that we build into the interpreter when we compile it. So the instruction set is basically fixed for all the programs you execute with this optimized interpreter. And what this means is, like, if we can have a quite simple example to illustrate this. If I just build an MLQ-style interpreter that only considers numeric optimizations, and I then let it run on some code that manipulates strings, it will not give you any noticeable performance improvement, because I estimated the utility of strings to be lower than the utility of numerical code. And so this, I think, is an interesting trade-off. You need a careful consideration of how real world code looks like, so that you can then fill these 2,000 instructions with interesting derivatives. 2,000 is an upper limit. In my research, I actually never had an interpreter with more than 600 instructions, and that already contained code for all the numbers, for Unicode strings, for lists and dictionaries, and so on and so forth. So this is about the best you can do. The last thought here on virtual machines, it's closely related to the information theoretic idea, is that CPython's instruction set originally is untyped, or a little bit more precise, is type generic. You see this binary add, it doesn't convey any type information. But MLQ basically, it it adds this implicit typing and data representation information to the instruction set, such that it now is type specific. And the way I like to think about this, and it's surprisingly effective in many other research scenarios, so I have at least 4 or 5 other papers that follow the same idea, is that you can externalize internal information, and that gives you then some more powerful abstraction over this. And I think this is also an interesting idea in instruction set design. There are unfortunately not that many people that do research on either instruction set design or intermediate representation. So I think most of the stuff there is still kind of folklore without any hard science and analysis there. So that's it. Some of the contributions, I think they are rather boring, so I'm not going to get into those, but I'd be happy to answer questions. I just briefly need to change to the video stream so that I can actually see what's going on. So now it seems to work, but it seems that my camera is off. Is it? Can you guys see me?
Not at the moment. You can see
I'm going to stop sharing. Okay. But I can go back to sharing anytime. I just don't see anyone else.
You can't see us.
No. It says I see 4 people. Ludwig Kanaba, Mark Betty, Benjamin Orcutt, and Joel Jakubovic.
Maybe I can change Olaf. So Olaf is a room camera.
Oh, now it works.
See how this put it like over this way.
They're actually
There's no camera on there. No, it's the thing on the wall. Oh, right. I can switch cameras, I think, but I don't know whether it's different. So, do we have any questions? I didn't have questions.
I have a question.
Wait.
So I wondered about the, does this kind of technique work only for languages that are kind of similar to the machine architecture already, or is this something that works, say, with more like functional code or something like logic programming? It seems like I got the impression that it's kind of specialized to certain types of language, but I could be wrong.
In that case, I'm not German per se, but I could be rather unfriendly, which is often associated with German traits. But so I think it said in the talk it's not restricted to functional and logic-oriented programs. So I think the way it's most easily understood is it should be a programming language that's high level in any sense of high level. So it's not so the stuff I showed here is just for Python, which is far away from the native machine, but it need not necessarily be. So for instance, you could use the same technique also to optimize Java, but the way you would optimize Java would not be to optimize away the types. It would much more be like to include some special case logic that you often use, for instance, some function call, some method calls you use repeatedly. So thus you could basically emulate polymorphic inline caching. So it's not really tied to. I think it works best for high abstraction level machines, but it's not somehow special. But then I can send you guys the slides, by the way. Yeah.
I think Dominic is interested in strongly typed languages like Haskell and things. Yeah. Perhaps as context. So where do you see the potential for these kind of languages?
I think it's quite high. So I have to admit it was not my own realization, but there was a person working on JavaScript core originally, and that guy contacted me once via Hacker News that he read some of my papers, and I sent him this MLQ paper in 2011 or so, and then he immediately made the link towards optimizing function calls in functional programming languages. So functional programming languages need to special case some logic to figure out what the best way is. And one of them, an interesting discussion, is in Xavier Leroy's PhD thesis, the Zinc experiment. He has like a chapter where he says, okay, this kind of function call is much more frequent than another one, so I'm optimizing this in OCaml. And I'm guesstimating that Simon Peyton-Jones or the other guy, the other Simon, I forgot his last name, I'm sorry. I think it was Simon Marlowe. Maybe not, I don't know. But I'm sure that there are some special cases there that you can also optimize with multi-level quickening, because you just basically say, oops, this is a function call that's curried, so I'm going to use this kind of logic, and for another case, I'm using something different.
Great, thanks.
And that should also work for logic-based, logic-oriented programming languages. So they have this clause indexing, and you could also special case on this. So it's not, it just depends on the machine you're looking at.
Do we have any other questions? So I found quite interesting your parallel with the Amdahl's law. So how did you go in practice about kind of assessing the potential for a specific benchmark? Did you measure kind of the time spent in an interpreter, for instance?
Yes. So I did. That used to be quite hard, but nowadays with Linux perf tools, you can do perf record with debugging information. And then in the paper that's belonging to this talk, I just grabbed some regular expressions that are fairly often used in the interpreters. You have to include a little bit more than the dispatch routine, some of the functions that are called there too, but you can easily distinguish the ones that are bound by the limited by the interpreter from the ones that are not. So basically, because that came up on, so I contacted the people from CPython. Carl Friedrich sent me a message. Carl Friedrich Bolz from PyPy sent me a message that they are discussing this again. And the first thing they asked me is to evaluate the benchmarks again. And one of them I immediately recognized is benchmark Django, where they just built an HTML table 100,000 times. And I remember this benchmark very, very very precisely, basically, because at one point I inlined the Unicode conversion code into the interpreter, and it still was not, basically was like 50% faster than the original one. And I said, by that I realized, okay, it's not something that's interpreter bound. It's just a benchmark that is, calling a lot through libraries and string conversion and so on and so forth. But it's not, MLQ by itself will not optimize this, because it's not something that's specific to the interpreter. So I would basically say, if you these Py performance benchmarks, the ones that I recognized, MLQ will do very well, but some others MLQ will do bad, and I think those are actually not interesting benchmarks. But again, this is something that I think is also true for spec. Spec benchmark suites is already quite old, and it has not been re-evaluated. So I think also for spec, it would be much more interesting to understand what the real potential for performance is.
Just to kind of follow up on that. So I have been talking to quite a number of Ruby people. And one of the things they always tell me, well, all these things are nice, but basically our applications don't do any addition. So I think what they see is indeed strings are one of the sources or one of the places where they spend time. The other is basic, really basic function calls, and it's all object-oriented code and a lot of indirection. So it's a lot of jumping around. So do you have any kind of perspective on that? So should we perhaps start redesigning our interpreters to be able to optimize these kind of use cases better?
I think you can. So back 10 years ago, I didn't look into Ruby because the source code was not really nice. So it's like Perl, but Perl is like the absolute, well, PHP is the absolute low bar for an interpreter. But so Ruby, I think, would lend itself perfectly well to this kind of work. And I think if you take a look at the Truffle guys that optimized Ruby, they got some nice speed ups there. So that's quite similar. And I think the only benefit of doing this on the interpreter level on C level is that you maintain A, compatibility, and B, memory is not an issue. So for some of the experiments, I didn't show it in the talk, but I think in spectral norm, my interpreter is actually using less memory than the original CPython interpreter. So I think the original CPython used 7 megs of RAM, and with this optimization, I only use 6. So in memory constraints, and if that is an issue, then I think also this MLQ style of optimization lends itself quite well to Ruby. Compared to Truffle Ruby also.
Do you have any other questions?
Sorry, I have a more basic question that I should have asked earlier. Sorry, which kind of maybe underlines my slightly strange question before. So the setup relied on having a notion of what we call instructions, which sounds like, you know, sort of bytecode interpreter sort of things, like Python has a bytecode format and so on. So it relies on having a sort of bytecode interpreted version that you're working on, right? This sort of instruction format. That's a sort of prerequisite. So you have your language and you have some kind of pre-compilation step into an instruction style format. Rather than say if I took like a pure Lisp file, which was all S expressions or something, that would structurally feel like very different to this approach, which is where my kind of question was coming from, like sort of mismatch in the structure of even just the basic structure of the program. So this is assuming you have some kind of like you're doing a bytecode interpreter style thing instead of straight from the language. Is that right?
Yes, yes. So I think it's primarily focused on bytecode interpreters. I also think let's say like this, if you take away the work on Truffle, I think nobody works on AST interpreters. So like even C Ruby and the other stuff, Perl is kind of a strange mixture, but most of them are bytecode based. So for S expressions, I think this is different. But if you take a look, for instance, in SCCD compilers or SCCD stack environment control dump style interpreters for functional programming languages, I think this is also something that could work well with those with this kind of optimization. It's just going to be different because you're not replacing the bytecode, but you could replace, let's say, computations.
Yeah.
And intermediate steps, yes. But this is super interesting, guys. This is highly recommended. Quite old, but I think it details all of the SCCD stuff and lots of optimizations there.
Great, thank you. Thanks so much.
You're welcome.
Right. I think on our end we are slowly out of time. And I don't see any further questions. So thank you very much for your time. Thank you very much.
Thanks again. Sorry for the technical problems.
No worries, no worries. I found it very interesting. I hope my PhD students also listen carefully.
Yeah, I can send you the slides afterwards if need be, or you like a link to the paper or so.
I think I probably have all the links, but I will have a chat with Octave who will try to drag into the dark side. So.
Okay.
All right. Thank you very much.
Thanks. All the best. Have a great day. Bye-bye.